Okay, so this is the final video on quadratic equations. Now this won't be the last time we talk about quadratic equations in this course. We'll definitely talk about them some more here. But let's go ahead and look at a couple story problems with this. So let's just go ahead and dive into it. So we have a story problem here. The floor of a one-story building is 14 feet longer than it is wide. The building has 632 square feet of floor space. And this particular problem I'm looking at gave us a picture of what this looked like. So basically this was W for width, and this was W plus 14 for its length. And then there was two questions. So part A, write a quadratic equation for the area of the floor in terms of W. And then part B is find the length of the floor. Alright, so let's go ahead and get going here. Now, I'm kind of going through the problem there, zoomed it far too much. We should recognize here, okay, we got a nice little rectangle here. And area of a rectangle, this is something we should all know, is of course just length times width. So we're just going to fill in the piece of information that we know. Well, we know that the area is 632 square feet. And this is equal to the length, which is W plus 14, times the width, which is just W. Now we'll go ahead and multiply that out a little bit. And so we have 632 is equal to W squared plus 14W. Now we'll just go ahead and leave it like that because that's a quadratic equation and it represents the area in terms of W. Now part B is we want to find the length. Now we know that the length is equal to W plus 14. So in order to find the length, we're going to have to find the width as well. So in other words, we need to solve this equation. But this is a quadratic equation, so we need to use the techniques we know to solve it. So let's move everything to one side, and I get 0 is equal to W squared plus 14W plus 1632. Not plus. What would I be doing here? I'd be subtracting from both sides, so it'd be minus 1632. That looks better. Alright, now we could go ahead and solve this however we want. We could try and see if it factors, but when it's something not obviously factoring, I typically go to either completing the square or the quadratic formula. And we'll go ahead and use the quadratic formula here. So just like I've always been doing here, I'm writing it out. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Alright, so let's go ahead and substitute things in here. So x would be negative 14 plus or minus the square root of 14 squared minus 4 times 1, so that's what a is, times negative 1632. And this is all over 2 times 1. And so this would be equal to, I'm sorry, this isn't x here. It's not really a big deal, but we should keep consistent. the variable we're using here is not x, it's what? W. Alright, so W is equal to this. And now we just have to, as I sometimes call, turn the crank and finish solving this. So W would equal negative 14 plus or minus the square root of 6,724. That's just simplifying everything up there, divided by 2. Now it turns out that 6,724 does actually have a perfect square root of it. This turns out to be that W is equal to negative 14 plus or minus 82 over 2. And so then what do we have? Well, we'd have W is equal to negative 14 plus 82 over 2, or W is equal to negative 14 minus 82 over 2. And so we get two answers for W, and it would be 34 or negative 48. Now, we have two answers, but we should ask ourselves that they both make sense. Negative 48 doesn't make sense in this problem, and it shouldn't take us too long to figure this out. We're talking about dimensions. We don't have negative dimensions. Dimensions are always positive. So W is equal to 34. Now, we're almost done here. We need to just figure out what L is. L, remember, was W plus 14. So L is going to be 34 plus 14, which when you write your final answer down, you have to be careful because it's 48, but we need to put units. And of course, since the area was feet squared, the units would just be feet. Okay, so we're going to look at one other type of story problem here. And this story problem actually is a fairly good representation of an application. This has something to do with physics. If you have had physics before, you've probably seen this. If you haven't, you'll see it again. This deals with the position of objects under constant acceleration. So there's a formula here, and the formula is S is equal to 1/2 AT squared plus V0t plus S0. And here A is acceleration, V0 is initial velocity, and S0 is initial position. And then S is position at time t. Now, positive and negatives matter greatly in this. If you're thinking about an object falling, if you throw the object up, that's going to be an initial velocity having a positive velocity. If you throw the object down, you're going to have an initial velocity that's negative. Now, since we're also talking about falling objects, we have acceleration due to gravity. And since things are going to be falling down, gravity's acceleration we can think of as being negative since it goes down. So there's two values that we can use. 32 feet per second squared, but then there's also negative 9.8 meters per second squared. And again, you can see clearly the only difference is one's in feet and one's in meters. I think we typically in these example problems are going to be using the one in feet, but doesn't really matter too much as long as you keep your units straight. So if we had a falling object, our formulas are going to be S is equal to 1/2 negative 32 t squared plus V0t plus S0, which would be negative 16t squared plus V0t plus S0. And again, this is if we're in feet. And we have one more equation, again, depending on what your units are. So the other one would be s is equal to 1/2 negative 9.8 t squared plus v0 t plus s0, which is equal to negative 4.9 t squared plus v0 t plus s0. And again, this would be if our units were in meters. Okay, so it does matter whether you're talking about feet or meters here. Okay, so let's look at an example problem here, and I believe, let's see here. Yeah, we'll let that, and then, yeah, we'll wrap up with that here, and then we'll move on to complex numbers, which, as we said, sometimes we can get complex answers for quadratic equations. All right, so let's look at this example problem. So you drop, I like to use black when I'm writing the example problems down. It's my little bit of OCD. So you drop a coin from the top of the Eiffel Tower the building height is 984 feet. And then there's three parts here. Use the position equation to write a mathematical model of the height of the coin Part B, find the height after 4 seconds. Part C, how long does it take before the coin strikes the ground? Okay, well, first off, the position equation we should be using for part A, this would be s is equal to negative 16 t squared plus v0 t plus s0. And we know we should be using that because my units are in feet. Now, we have to ask ourselves, what is v0, and then also what is s0? Well, we're dropping it. So we're not throwing the coin down and we're not throwing the coin up. Since we're just dropping it, there has no initial velocity on the coin, because you think you have it in your hand and you're literally opening it, and so it has no initial velocity. Once you open it, it's going to immediately start getting velocity, but as soon as the moment you precisely open your hand to drop the coin, it has no velocity. So our initial velocity is 0 feet per second. Now the initial height, well, they give us that in the story problem. The Eiffel Tower is 984 feet tall. So then our equation here would be s is equal to negative 16t squared plus 984. Now part B is pretty straightforward. Part B is just wanting to know, when is this thing equaling, what is the height after 4 seconds. So after 4 seconds here, we just plug in 4. So s is equal to negative 16 times 4 squared plus 984, which would be negative 16 times 16 plus 984, negative 256 plus 984, which would be 728. And again, you want to put units on it, so it'd be 728 feet. Alright, one last part here. We want to know how long it takes for it to strike the ground. Well, in order for it to strike the ground, the height here would be 0. And so we're just solving 0 is equal to negative 16 t squared plus 984. Now you could use the quadratic formula or something to complete it, but since there's no t term, we can actually just solve this pretty straightforward by first adding 16t squared to both sides. So you get 16t squared is equal to 984. Divide both sides by 16. So we'd get t squared is equal to 61.5. And then t is going to be plus or minus the square root of 61.5, which it makes sense that we should only talk about the positive time and not the negative time. So the time is 7.84 seconds, because I approximated what that square root was to 2 decimal spots. Alright, so this wraps up our videos on the quadratic equations. As I said, we will talk about these more later on in other videos. So we will be moving on to complex numbers.